Okay, so thank you for taking the time to at least open the first few seconds of this makeup lecture. I hope that you find the material here valuable and worth your time to listen to, as some of the rest of our class will be based on understanding of these more complex styles and types of airfoils discussed after we made it past the basics. I do believe this is the slide we left off on, where I had a little bit of a hurried explanation of Reynolds number effects on airfoils. I don't want students to think that everything about an airfoil changes only due to Reynolds number. A lot of the non-dimensionalization we do into coefficient of lift, coefficient of drag is very, very, very useful for modest changes in speed, for comparing things against different velocities, different flight ranges, etc. But sometimes when you're getting too disparate from the original case in which you've tested something, it is important to make sure that the underlying aerodynamic qualities have not changed due to Reynolds number. If you had to model Reynolds number and Mach number every time to make bookkeeping coefficient of lift and coefficient of drag useful, then it actually damages their utility, and it might not be as beneficial. But we certainly use them all the time. We can carry on with a little bit farther discussion of boundary layer. Just another reminder: we've seen this chart now probably 2 or 3 times. I've even drawn different velocity profiles on the board during the first lecture, but your text actually has a discussion that goes into some of the boundary layer viscous fluid dynamics. You're welcome to take a look at that. Don't feel bad if the equations scare you away. It's perfectly fine and expected for an intro-level aerodynamics course. But this does show that it does depict the transition between laminar, transition into a turbulent boundary layer, as well as separated wake region. You can imagine if we were looking at a circle, a sphere, a cylinder, instead of an airfoil, you'd have a much larger wake region, and then the understanding and ability to model transition would dominate where that flow actually attaches to the sphere, or if it detaches immediately when it hits, pi over 2 radians or 90 degrees from the stagnation point on the front. It really changes things quite a lot. So definitely a worthwhile thing to understand, and if it really captures your engineering imagination here, I would suggest definitely taking viscous fluid dynamics, because you can understand boundary layers more fully and then take advantage of their dynamics to your benefit as an aerospace engineer. We had mentioned but not talked in depth about NACA 5-digit airfoils. We've already mentioned that they're more complex airfoil shapes with more sophisticated profiles. They do follow a bit of rhyme and reason, though. The first digit, as it says right in front of you, when multiplied by 0.15, which is kind of a random coefficient to remember, but it'll make sense here in a little bit, gives you the optimal CL. Now that's the probably single most useful component of the 5-digit series. Aside from the fact that they're good profiles, they have appreciably low drag. They basically represent an advancement in airfoil technology beyond NACA 4-digit series. The fact you can dial an optimal CL just by changing one number shows how much thought they've put into just the empirical and other mathematics inherent to the 5-digit series of airfoils. So if you see first digit is 1, you know that airfoil will have an optimal CL of 0.15. 2 will be 0.3, 3 is 0.45, etc. And what that does is place the drag bucket. It changes camber, and it adjusts the foil shape so that its optimal low drag region is right on the designed lift coefficient. And we'll see that in the following slides. Second digit, multiplied by 5, gives percent core to max camber. Okay, that's very similar to the NACA 4-digit. Third is a switch, essentially. Simple camber is what we'd expect in a normal airfoil. Reflex we've discussed as you saw the flying wing slides. That's where the trailing edge flips back up, and you see a reduction in the total coefficient of moment created by camber on an airfoil. And then lastly, of course, the 4th and 5th digit are the maximum thickness of the airfoil, which has the same effects that we've discussed on the NACA 4-digit foils, namely prolonging of attached flow, delay of stall, and softening of the stall by forcing it to occur first at the trailing edge of an airfoil instead of the leading edge due to a sharp profile. So the biggest change here really is the ability to turn the switch on and off between simple camber or reflex camber. Mainly the third digit makes it a flying wing airfoil or makes it a standard type airfoil. Then the first digit gives you the ability to, without even running pressure distributions, without running X-foil or any type of software, it lets you directly choose the optimal CL for the airfoil. So it's very useful. It does have a similar set of equations that describe the airfoil shape. These are the camber lines for non-reflex and reflex. This is what that third digit switches on and off. It chooses between these two piecewise functions. Again, you'll see that the non-reflex goes from 0 to P and P to 1, so different regions of the foil. There's one curve defining the front, from the leading edge back to the maximum camber location, and then P to 1 will be from maximum camber to the trailing edge. With reflex airfoils, you see the coefficient R, and it's a similar type of story. The tool I'd recommend is not to go out and write your own Excel file. It's not to go out and write your own MATLAB code to make 5-digit foils, unless that's just your fun on a weekend. I would suggest hit up Airfoil Tools again. They have NACA 4 and 5-digit tools. This really is a website that is relatively new in the scheme of aerospace and contains a lot of information that used to be spread all across the internet, all across different references. So that's why you hear me talk about it so much. Perhaps you've been convinced so far that already that it's a good thing to go check out. If you haven't, then you'll probably hear me talk about it a couple more times. But it can generate NACA 4-digit, 5-digit, and some higher order foils, both with reflex camber lines, without. Lots and lots and lots of good shapes can be generated this way. And if they don't already have a pressure distribution for that NACA foil, you can always grab what's called the DAT file. You see it here in this region. I think I should be able to draw here. Yeah, nice. Let's draw with a pen. The DAT file. Yay. Undo. No. You'll be able to bring those points into X-foil and run your own pressure distribution once we cover that in the next lecture, which I suppose will be Tuesday. So after you're making it past airfoiltools.com and things like that, it starts time to talk about some novel airfoils, some different types of shapes. And kind of the goofiest, strangest family of airfoils that still isn't as terrible as the shapes might lead you to believe is Klein Fogelman. Primarily, these are made for easy construction. Quite honestly, they came about because somebody wanted to make a foam RC airplane, and they wanted to make a very easy, simple wing. So if they crashed, or if they got in a dogfight with a friend, if they collided with a tree, whatever, they could make a new wing really, really fast by just bending foam board around itself in various ways. So that's why you see all these stepped construction methods. Obviously, a flat plate offers you no camber, offers you limited aerodynamic performance. But if you start investigating the actual real-life performance of stepped airfoils like the Klein Fogelman, you have all the KFM1 through the KFM9 depicted there on the right. You get some interesting performance. It's not entirely terrible. I mean, it's not great. You certainly do better by doing a molded type wing if you have the facilities, money, and time to do it. But if you just want to make something fun for a weekend to go out and fly without much of a problem, these are good. The one downside I will warn you about is some students will try to take these airfoil profiles, load them into X-foil and similar codes, and they have trouble getting them to what's called converge. You have trouble getting a valid solution because if you see in the CFD solution down at the bottom, there is a distinct region of recirculation. Use my magical pen again. When I say recirculation, I'm talking about this almost doorstop shaped loop of fluid. That's exactly what's happening. It's kind of like the classical reverse step test case for CFD. So you see that in the flows consideration, these are streamlines. Maybe the shape isn't quite as bad as the outline makes it out to be. If this region of recirculation is just spinning, yet the flow around that region is staying mostly attached. It's almost like an aerodynamic wedge that keeps it smooth. But like I said, in most cases, almost every case, this will be outperformed by a classic airfoil. It's just a super low cost, super easy to make airfoil shape. And you can see there's plenty of iterations. So that's Klein Fogelman. You hear somebody speak of it, that's what they mean. Transonic shocks. Now we're getting to the interesting part of aerodynamics. The unpredictable, the high-level math, the portions of flows that take CFD and other high-order methods as a requirement to determine how things work. So transonic shocks form whenever the aircraft itself is flying at high speeds already. You're not going to form transonic shocks, as you're leaving the parking lot in your car. There's just not enough energy in the flow to accelerate that much naturally around the body. But if you're in a 737, if you're in a commercial airliner, there are absolutely, most every time they fly and cruise, transonic shocks that exist somewhere on that vehicle. We'll discuss that more when we get to Mach drag divergence. But oftentimes around the engine nacelles on the top, perhaps around some vortex generators, winglets, some small locations of the aircraft will definitely generate small shock waves. And you tow them along with you the entire way during cruise if that aircraft is really pushing it in matters of speed. But what forms transonic shocks is when the airfoil, in this case, only considering the airfoil, it's only two-dimensional, the airplane doesn't exist, it is only an airfoil. If you reference the CFD depiction in the top right, which is important because this is very much a compressible flow scenario. You're above Mach 0.3, which is the Mach number at which we assume that flow can now be compressed just by the presence of a body passing through it. So you can see the flow actually slows down tremendously right in front of the leading edge. So V infinity is roughly Mach 0.8 in this case. It actually slows down to about Mach 0.7 if you look at the color scale. But then something interesting happens around the foil. As the flow is accelerated around the top and a little bit around the bottom, you actually see that it goes supersonic. There's not a shock wave as it starts going faster than the speed of sound. It's actually expanding. The flow is expanding and being encouraged around the foil. So you hit a Mach number about 1.3 and a little bit higher. I guess the highest in this region that's indicated by the color swath is 1.411. But then the bad part happens. Then the world comes crashing down. Physics comes crashing down on top of your head. At the overlapping black lines at the aft portion of each one of those supersonic flow regions. That's where, due to the basic shape of this airfoil, due to the flow acceleration imposed, due to the thickness of this body being pushed through the two-dimensional flow case, you create a shock wave. The flow no longer expands, and you create a discrete shock at the back side of those supersonic flow regions. You see one forms on the bottom of the airfoil where things seemingly stack up. You see one forms at about 85–90% chord on the top side of the airfoil, all these stacked regions. So just to be clear, since I do have my magical red pen, we're talking about these stackings of Mach regions. So you say, okay, so what? Why do I care if there's a shock wave there? First of all, you generate supersonic drag because of the presence of that shock. Secondly, as depicted here in this image, it generally will separate the boundary layer. Right where the supersonic shock happens, due to this very classically designed, almost NACA 4-digit symmetric foil shape, you get a very, very strong shock wave right there, about 50% chord. The flow instantly goes back to subsonic, and the boundary layer itself separates. So you get a lot of what's called wave drag due to supersonic flow effects. Your engine is now losing energy directly to the flow surrounding the plane due to shock wave, and you're separating the flow behind it, making the situation even worse. But as we've already switched to the slide, there's an answer, and it's not so bad. It's called supercritical airfoils. So for a while, there wasn't a whole lot we could do about the presence of transonic shocks. Planes would start going appreciably faster, start going with the jet age and some very high-speed propeller aircraft. It was starting countering these, and it would take more and more power to gain just a little bit more speed. In fact, in the case of the P-38 fighter, they almost doubled the engine horsepower. I think by the end of World War II, the plane had somewhere with two engines combined on the order of like 3,000 horsepower, which was a lot, especially for that day and age. But over the course of doubling the horsepower of the airplane, they went 20 knots faster, 20. They added 20 knots to the total maximum speed of the airplane because this creates so much drag. They kept pushing and pushing harder against these transonic shocks, and honestly, the shocks were winning. Just pouring fuel into the engines with little effect on the maximum speed. So NASA, in fact, this is the supercritical wing testbed aircraft depicted above. An X-plane is a modified Corsair, previously a Navy fighter. Very recognizable by its giant air intake, which on more than one occasion swallowed a person on the deck of an aircraft carrier just because of the breathing in so much air. Yeah, you can see videos of that. It's on YouTube. I think the guy lives. That's the only reason I mentioned it. But what these transonic shocks, or excuse me, what these supercritical airfoils do to transonic shocks, are they shift the camber towards the back of the foil. If you notice here in the bottom here, the depiction 2 of the airfoil, you still get a region where the flow goes supersonic. You're still generating lower pressure, and the reduction of pressure usually, especially when you take into account Bernoulli, means that you've accelerated the flow in that region. So if you come in at Mach 0.99, you reduce the pressure, you've accelerated the flow, well, guess what? At some point, it's still going to go supersonic over your airfoil, even though your entire vehicle remains at a subsonic speed. That's the thing to understand here. We're just locally accelerating the flow. The whole airplane might be going Mach 0.8. But if you're working the air, meaning accelerating it sufficiently enough, you could have Mach 1.1, 1.2 flow in certain regions. But what a supercritical airfoil does is it allows that flow to reconsolidate into a smaller shock wave at the aft portion. It keeps the camber line of the airfoil mostly neutral until the back, where you see now it kind of comes up and back down. That's a terrible drawing. I'm doing this with a mouse. You hopefully understand. So what that does is makes it where you can still generate positive lift at 0 alpha. Your airfoil still has a net positive coefficient of lift at 0 angle of attack. It still has very low drag due to the shape of the profile, but most importantly, it does not generate the strong shock wave as seen in scenario 1 above. If the flow around the foil has to go supersonic, the goal is to reduce the strength of the shock wave and to put it as far aft on the airfoil as possible. That way, if it does separate the boundary layer, if it does create a separated region, it's not that big of a deal at that point. So, supercritical airfoils, if you need to punch through transonic a little bit easier, if you need to raise your drag divergence Mach number, that's the way to go. Generally a high-speed scenario, hundreds of miles an hour. You're not going to have to worry about this at low Mach number. Which brings us to flaps, another components you can add to airfoils to improve their lift. Now, granted, the picture I'm showing here in the bottom right is a 747, if I'm not mistaken. Quite confident in that. Airbus probably has its equivalent, but I'm quite confident that's 747. That's a wing implementation of triple slotted Fowler flaps. If that name is totally foreign to you, that's fine. Don't fret it. We're about to teach you what that means. But you've seen complex apparatus like this make its way onto airplanes. Anytime you see something complex put onto an aircraft, you know it really has to be worth the weight, engineering time, fatigue, and just all the penalties you pay for very complex mechanical systems to be implemented. Nothing about that arrangement you see in that photo looks simple. In fact, this picture you see depicted up here on top, the series of airfoils placed one after another, 1, 2, 3, 4, 5, 6, 7 through 8. This is an interesting study that I always like to introduce students to first when we discuss flaps, because, well, if airliners often have 2 or 3, would 4 be better? Would 5 slotted flaps be better than 4? Would 6 be better than 5? And here's your answer. It's all about pursuing higher and higher coefficients of lift. So you can see here in the right, this is the accompanying graph from the study shown at the left. They took a profile and started adding more and more and more airfoil shapes to it. They call it kind of the Venetian blind experiment, if you know that style of blind from a house or a window. So without any slot, the condition you see here, no slotted flaps, the maximum coefficient of lift of this section was 1.6. At an angle of attack of, let's see here, that was about what, 14, 15? So they added 1 slotted flap, and hey, you got an improvement. 2 slotted flaps, you got another improvement. But see, it's also continuing the continuing the lift curve slope to higher and higher angles of attack. So now the CL max occurs at, which CL max is approximately what, 2.1 at this case, happening at 28 degrees. And so 3 slots, 4 slots, 5 slots, 6 slots, but then 7 goes back down. So in this study, with these particular circumstances, in this particular test case, 6 seemed to be the magic number. I wouldn't take that all the time, but for this scenario, it happens to be that case. You see that you almost reach a naturally occurring coefficient of lift of 4.0. I mean, with a default airfoil, you're doing very, very good. Without any flaps, you've reached 2. So something is happening with these slots. As you continue to add slots for air to pass through in these Venetian blind type arrangements, you're able to reach higher and higher coefficients of lift. This comes with penalties. You'll understand more so whenever we get to 3-dimensional effects, but it's an important result to see at first. There are many types of flaps. The basic section is what we're start with. The plain flap is what you might see with an aileron or a control surface on a vehicle. It just pivots around a hinge. There's usually, if I can just place one little red dot, a hinge that goes through the airfoil right there. It's connected to control rods and cranks, and this all goes back to the pilot's control stick, hydraulic actuators, or whatever else is controlling the plane. This offers, the plain flap, I should say, offers a very low drag penalty for changing the coefficient of lift of the section, because that's really what these flaps are doing. In each scenario here, you see them going down, but a plain flap as a control surface can just as easily go back up. It can be deflected up, just as easily as it goes down. A split flap, however, is just usually only on the bottom of the vehicle. Normally, these are just deployed on landing, so adding a bit of drag can sometimes be advantageous. And well, if you open up this giant V on the back, yes, congratulations, you've made a whole lot of drag. So much so it continued off the slide. So split flaps, useful, very simple to implement, very simple mechanically. So you see them on small aviation airplanes, you see them on some bush aircraft. They can be lightweight to implement. Still leaves a lot of structure, some continuous structure here above it. So, I mean, you find them, but oftentimes only in scenarios where the designer is not concerned about the drag, the additional drag that comes from deploying a flap. Now we get into the slotted flaps we were discussing on the previous chart, the Venetian blind type experiment. You can't have a single slotted flap, which is what you see depicted here. It's where the control surface, similar to a plain flap, is deflected up or is deflected down, but in this case it has a gap, an intentional gap in front of it that allows air to flow through. And what really happens when you look at flaps, slats, all these different types of leading and trailing edge devices we're discussing now, when you look at them in a real flow scenario, they work great until you start separating the flow due to deflection. You can't deflect these surfaces 90 degrees straight down. You can't put a plain flap straight vertical and expect the flow to remain attached to it, turn that 90-degree corner without issue. No, I mean, the boundary layer will separate. You just get a ton of drag and very little increase in lift. So a slotted flap actually uses the passage of air through this gap to re-energize the flow, to essentially restart the boundary layer at a somewhat new stagnation point on that flap. So then it starts undergoing the same adverse pressure gradients and similar flow scenarios that we've discussed with airfoils in general. But overall, you get a net benefit to the deflection angles, to the lift coefficient you can get from this net system by allowing some of this higher pressure flow from the bottom side of the airfoil to pass through and do its job of helping to keep the flow on top attached. So again, compressing or continuing in complexity, a Fowler flap. Now it has a very particular name. It is really just a cheaty slotted flap, because what they do in this case, they do allow the gap to exist. It is just a plain flap in most considerations. Normally these will only drop down. Fowler flaps start to get into systems you might only use during landing, not really used for maneuvering, hardly ever. But I say they're a little bit cheaty because they bookkeep their CL without telling anyone. They just increase the chord of the wing. Look at all the other flap scenarios here. So the basic section has so long. Whenever this Fowler flap is retracted, the airfoil might be 1 unit, but whenever they extend it, it actually moves mechanically aft. So the chord length of the airfoil changes. Generally, we don't model this chord length change as we study the deployment of flaps. So they get to essentially add area to the wing without really modifying the reference area of the wing. So yeah, it offers a distinct advantage in the amount of lift that section can generate. There's nothing really cheaty about it. It's just I want you to know that they do not keep the chord length changed for the deployment of Fowler flaps. It's just all considered a part of the coefficient of lift of that flap system. So now if you combine the best of all of these worlds, you get into slotted Fowler flaps. And these are the systems you see employed on most commercial airliners. In the early 80s, late 70s, maybe in the 90s, you saw a lot of triple slotted Fowler flaps. You saw a lot of more complex mechanical systems. But as reliability became more important, as safety became more and more important, metal fatigue, mechanical systems, and overall aerodynamics as well just became more understood, you now see a lot of aircraft deploy either a single slotted Fowler flap or a double slotted Fowler flap on the trailing edge. Seldom do new aircraft come out that have a triple slotted Fowler flap, just because each additional mechanical segment you have to have in that cascade complicates the arrangements. So that's kind of the progression from simple and cheap to complicated but very, very high lift. And that's really why you would make this trade-off. You don't have to go to a slotted Fowler flap if you don't care how long it takes for you to take off. You can take a basic wing section, leave your engines on full thrust on the runway for another 3,000 feet, and then take off with a lower coefficient of lift. Just go faster before you try to take off. Flaps are deployed to raise your coefficient of lift so that you can generate the dimensional force you need. If your airplane weighs 1,000 pounds, you have to make at least 1,000 pounds to take off. So if you have a higher coefficient of lift, that means you need less v squared to leave the ground. That's what they're hunting with these flaps. It's easier to land if you're going slower. It's easier on your tires and your mechanical systems. You can have a shorter runway. It's kind of the same advantages going the other direction at takeoff. Plain flap, control surface. Yep, pretty much just said all these things. One thing that bullet point points out that I did not refer to is that really you are just changing the camber line of an airfoil. You have a discrete kink in the camber line there, in this case about 80% chord, and oftentimes that is controllable. You can have active control of the camber line of a surface. There absolutely are airfoil systems that are investigating, researchers that are investigating a more organic camber modification system where the whole airfoil will more or less flex, where it would change shape, a morphing control surface instead of a discrete mechanical hinge. That's certainly being looked into and does overall offer some drag benefit. Split flap. We discussed these systems. This is another handy chart that comes out of a textbook I had to reference. This chart below shows what coefficient of lift was determined as the trailing edge. So the trailing edge of that split flap is deployed to different locations. You see as it goes farther down, the net coefficient of lift increases. And just generally gives you an idea of how the overall coefficient of lift is modified. Like I've said before, all the comments I made about split flaps still stand. One good comment is that these are very useful for solar-powered aircraft. They like to use these because on a solar-powered airplane, you have the top surface covered with, well, solar panels. The sun is up high. So you put them on top. It's a no-brainer there. But it's also more difficult if all of a sudden you say, okay, I need to chop off the trailing edge and put in control surfaces now. The design crew looks at you very angrily and says, no, you're not chopping through our solar cells. Figure out a different way to do it. So split flaps step in and become employed in solar-powered vehicles. Fowler flaps, there's another close-up example in this case of a 1-slot, 2-slot, and a 3-ish. We'll call that a triple slotted Fowler flap. And again, you see these mechanical systems fold up that flap entirely inside, as depicted here in the top right image, inside of the airfoil during cruise flight. You don't want to deploy that flap system when you're trying to go fast. It is definitely an obstruction. It's definitely an increase in drag. Additionally, one thing to mention is that they're very noisy. At each boundary of this flap system, so There's an edge, there's one more edge, here's an edge, there's a giant stick out in the flow, a giant hydraulic actuator handle. There's the back face of an aerodynamic device. Here's an open front face. They're aerodynamically very dirty. They disrupt the air and create everything but smooth airflow over those aerodynamic devices. What this generates is noise. And as you might have heard, the FAA, NASA, and a lot of other subjects are trying to decrease commercial aircraft noise to make them less of a burden on residential areas that built up around airports and then complain that airplanes are flying over. Right. So reduction of aircraft noise is an important focus, and there are some target goals put out for the future of commercial aviation. We'll see if they achieve those, and overall it has been part of the motivation to reduce the number of slotted Fowler flaps. So that's another reason you might choose a double slotted flap over a triple slotted flap, is that it would be quieter. So lots and lots of reasons and distinctions to use different kinds of flaps. One other thing worth mentioning before we deviate too much farther is that let me draw, with a terrible mouse drawing here, on this deflected flap, the chord line now. So that's the front, this is now the back. So even if your aircraft, that's not bad, even if your aircraft is level in the sky, you now, due to the deflection of your Fowler flap, have an angle of attack, because the chord line is defined as from the leading edge to the trailing edge, and well, you just dip the trailing edge about 2 feet beneath the actual rest of the part of the wing. This is beneficial because it lets the fuselage of the airplane come down level, makes your passengers all comfortable and not worried about anything. You don't have to lift the nose far, far, far up to generate high coefficients of lift. And you saw in some of the other charts, these CL max values aren't reached until 20, 25 degrees. People would be concerned, to say the least, in the cabin if your commercial airliner tipped up to 25, 30 degrees to land. Not to mention your gear would have to be taller, the angle of retraction on the back of the fuselage would have to be more steep. It would just have many impacts. So by dropping flaps, you're changing essentially the incidence of the wing, the mounting angle of the wing. You're changing its default orientation on your fuselage so that everything about your airplane stays level, while you get this nice benefit to angle of attack because your trailing edge just dropped down. It's kind of the same effect as just rotating your whole wing around some pivot point as it sticks through the fuselage. Spoilers, they make drag. That's their job. That's what they do. In some occasions, especially on gliders, high-performance sailplanes, which is what the picture is up top you see, they install a spoiler on the wing intentionally to reduce the lift-to-drag ratio. When they come into land, they don't want to glide 30 feet forward for every 1 foot they descend. It's easier to land if you have a bit steeper profile on occasion. Spoilers primarily exist to trip the flow, to separate the boundary layers. You see, I've put this depiction down here that shows where the spoiler exists, and the flow behind is just terrible. This can be used for yaw control. If you deploy only the left spoiler on an airplane, well, guess what? You're turning left. If you deploy only the right spoiler, guess what? You're turning right. So it all makes sense. We've already discussed double and triple slotted flaps quite a bit, but it's also interesting to see that you can have slots all over the wing, and it still does a pretty good job. This is an interesting depiction from another textbook to reference. It's in page 229 of Theory of Wing Sections. If you look at CL max, the plane airfoil section with a deployed flap, there's a CL max of 1.95, but if you look at some of these other arrangements, there's a 2.4, 2.1, 2.5. There we go. Let's just build that guy. A bit wild, but you can certainly devise some sort of theoretical mechanical system that can make that happen. There's 2.6. Some systems that really seem outlandish, but there's no reason that couldn't be made in a real airplane if you wanted to achieve higher CL max. Now also look at what happens to the drag coefficient. So it's just a plane deployed flap. You have a lift to drag ratio in this configuration of 128.2. Keep in mind, that's just the airfoil. My goodness, if we could achieve that on the whole airplane, we'd burn way less gas. But if with these different configurations, you pay different penalties in overall lift to drag ratio, which is something to consider whenever you deploy flap systems. It's the same reason you don't want to cruise around the sky with them, because they generally increase drag significantly. So Freise ailerons, these are another interesting arrangement, another control system, another method of modifying your camber line. As the first bullet says, this solves a problem I haven't even told you exists. That's a problem of adverse yaw. If you have a large wingspan airplane, we've already studied that as you add camber to an airfoil, as you essentially deploy the flap down, in this case, if you have control of it, you will increase the coefficient of drag of that airfoil section. So let's say your airplane drops the control surface down, trailing edge down, on the right-hand side of the airplane, the starboard side. Well, drag is now increased on that portion of the aircraft. You're doing this in order to try to roll the airplane to the left to generate what would be called a negative roll rate if you do the right-hand rule out the x-axis leading out the nose of the vehicle. So you're trying to roll the airplane left, but you drop a flap trailing edge down on the right wing to lift that wing up, generate more lift on the right side, generating the roll you want, but you've increased drag. This asymmetric drag creates a yawing force on the plane. So the fact that you have more drag on the right side now will pulls the nose of your vehicle towards the right. It generates essentially a positive yaw rate. So Freise ailerons in a mechanical system help oppose this change. Whenever the aileron is going down on a Freise system, it's pretty typical. There's nothing so strange about that. The special nature of a Freise ailerons and where you put its hinge line is the special nature of it. Notice it's rather far on the top and rather far back on the control surface. Whenever it deflects up, meaning in our example on the left side of the aircraft, the side of the wing you want to reduce lift on to generate your roll to the left, it intentionally sticks out into the flow. So all this air hitting the front leading edge of that aileron section is now just drag. It intentionally creates aerodynamic problems to match the increased induced drag, the increased drag of deploying a flap down on the right-hand side of the plane is matched by the profile drag generated by putting the aileron up on the left side. This will be a little bit easier to understand once you get to three-dimensional effects of wings, but overall, it intentionally creates drag only when actuating in one direction, namely whenever the trailing edge goes up, drag of that airfoil section increases. So all these discussions so far have been about the trailing edge. There's plenty going on the leading edge of an airfoil as well. In fact, in many cases, these effects are much stronger, especially for smaller devices. One of the most effective tools used in bush planes is shown here in the top image, called a fixed slotted flap. They will, quite literally in this case, just rivet on a fixed slot up front, and you get a massive benefit to CLmax because of this. They do have other options as well. You have leading edge cuffs, you can have leading edge flaps that droop down. That one's not such a glamorous option, we'll call it. And movable slot is fairly common on commercial aviation. You will see them deploy and then retract a movable slot at the front of an airfoil as they take off and land. That way they still get the low drag benefit of a clean airfoil during cruise, but they can generate very, very high coefficients of lift on landing. We've discussed this a couple times just in passing about the names of blown airfoils, boundary layer control. That's what BLC stands for. This is a research area that has had a lot of money put into it. There's some very interesting aerodynamic things happening here, but overall the biggest penalty of this is the hardware, the mechanisms, the added complexity and added possible failure points involved with establishing these blowing and suction systems. So you can imagine it's essentially a large vacuum cleaner attached in the first case. If you're going to ingest the boundary layer, which is getting thicker as it flows along the top of the airfoil, you literally have to suck it into the middle of the airfoil itself, and then inject that air elsewhere on an airplane. This works to help reduce drag because it keeps the boundary layer thinner, keeps it attached, and can do some very novel aerodynamic things as a result. But again, overall, it comes with a noted system weight. The opposite can also be true if you have a high-pressure air source, namely bleed air from an engine or high-pressure air coming from somewhere else in the vehicle. You can nozzle it out. You can squeeze it out through other orifices in the top side generally, because that is the problematic boundary layer side of an airfoil, to re-energize the air. You essentially add kinetic energy to it to, again, keep the boundary layer thin through different flow mechanisms and keep it attached to the plane. Both of these are used with interesting effects in modern aircraft, not employed, as far as I know, on any commercial products yet. And that's not to say there haven't been plenty of experiments with these type of systems. In a little bit different mechanism, the QSRA, the quiet stall, no, not stall. Well, it's essentially a very high lift research aircraft, QSRA. Apologies for going blank on the name of that. But regardless, it generates some of the highest coefficients of lift seen in any aviation system to date. Now, the first thing you notice is that the engines, well, they're on top. This is part of the research program that led to the development of the C-17, another very short takeoff aircraft. You see C-17s on the same chart over here, and this is an interesting chart to look at. These are all pretty much transport aircraft. And you see the development from the Fokker 100, which is a World War II era plane with a CL max of 2 point something. You see the C-5, which is a very, very large cargo airplane in the U.S. inventory with a single slotted Fowler flap. That's what the SSF stands for. I have the key down there at the bottom. You progress to double slotted Fowlers, you see you get a little bit of an increment in overall CL max. You get triple slotted. Well, there's another advantage. So the 737 has triple slots. 747 has them, but honestly didn't do that great of a job designing them. Then you get over to the C-17. This is when you're in powered lift systems. The C-17 blows engine exhaust directly on the flap system sitting right behind it. If you think that sounds really hot, you're right. They have to very much beef up the structure. They have to definitely take thermal effects into account, but they can reach at times coefficients of lift approaching 5. If you look at commercial natural systems, even with very complex mechanisms, they're still below 3. The YC-14 is again a test aircraft. Leading up to the C-17, it did even better, reaching almost 6. Well, but then there's the QSRA that achieved similarly high levels of lift. And what's happening here is you're energizing flow over the top. You're taking the entire engine exhaust and using the wing to redirect it. So you're taking all the momentum that leaves the backside of the engine, redirecting it with the wing. There's a little bit of Coanda effect being considered there, which is a term you can look up if you really want to read a more complicated description of Coanda. Means it follows the surface it's attached to. But it's a direct powered lift system. Just because the engine in this circumstance isn't pointed towards the ground doesn't mean the exhaust of the engine isn't pointed at the ground. Plus, what do we know about high speed flow? The pressure in that flow is generally lower than free stream. So by shoving a lot of high speed air over the top of these airfoils, they generate a lower pressure region. And it quite literally, you could think in a certain way that it sucks the airplane up into the air due to powered effects. Again, the downside of this is if your engine fails on takeoff, well, at best you're going to be surprised back down here and probably be in for a very hard and flammable landing. So this brings us to one of the last slides where we would talk about wind tunnel testing of airfoils. Now this is a nice transition when you start to talk about 3D effects, because you look at this picture and you say, those are wings. Dr. Hayes, what are you talking about? This is a wing. I see a wing in a wind tunnel. But the fact that they travel from wall to wall means that the air flowing over them sees zero end effects. You know, aside from the fact they have giant aluminum plates strapped to that one, and they have big winglets here for that. You know, nothing is perfect. You do the best you can in a test environment. Actually, this scenario here earns a red star because they probably seemingly did the best at incorporating that test airfoil section. So the fact that the walls are present keeps the flow aligned and keeps it mainly two-dimensional. In the aircraft coordinate system, we call that flow predominantly changing in only the X and Z directions. That's what we want. That is the two-dimensional flow we've been talking about with airfoils. This happens because of a theory called image plane theory. In an actual wind tunnel, if we take this red curve for a moment, the flow is definitely going to slow down next to the walls. There's the no-slip condition. You want it to be rather uniform across the center section, but okay. Reality steps in and says, well, against the wall, it's going to slow down. You make it as good as you can. So that's one caveat. We'll put an asterisk on this consideration, and you can just keep that in mind. But what happens in this scenario, what allows you to consider this as an infinite airfoil, is that the presence of a wall forces flow to always be tangent to it. I mean, air moves along the wall. That's not a surprise. It's a commonplace thing. You cannot pass air through a wall. So mathematically, if you wanted to express the presence of an airfoil in this environment, you might as well, instead of trying to model the airfoil and trying to model these rigid surfaces all the way around it, you can simply put another section of the airfoil next to it. And well, since this virtual tip might now be considered at that location, the effects we might expect to see of wingtip vortices are, well, not as effective in this region of consideration that I'm scratching through right now. This is going to get really messy really quick. Can I remove all that? Ta-da. So what ends up happening is you have an infinite series of mirrors, theoretically. A rigid wall, whether it's a wall in a wind tunnel or the runway on the ground, acts as a virtual image, reflecting. It's like a mirror. It reflects whatever is on the other side of it. And once you get into potential flow theory and fluids or aerodynamics, once you get into some introduction to CFD, you will see mathematically how true this actually is. You end up with a virtual mathematical image of the same flow scenario on the other side of the image plane. It's really a very, very handy phenomenon, and something that allows us to take a total wing and test airfoil effectiveness without worrying about three-dimensional effects around the tips of the airfoil, and compare one shape to another in a real-world test environment. So, that brings us to the end of this lecture. I don't really see a counter. Hopefully I didn't go too long. I'll be curious to see how long this video is. Thank you if you watched this whole thing. Hopefully what you learned from it, or things you learned how to look into, are worth the time you spent listening to it. I will see you soon.